Okay, so let's see some miscellaneous examples next. We have a function here, a real function whose domain is the set of real numbers itself. And the function rule is f of x is x plus 10. We have to sketch the graph of this function. So that means we have to make a table. Now, of course, we have already drawn such graphs many times in lower classes. And you may probably know that since we have only the first power of x, namely x itself and no higher power, there is no x square, x cube or any other higher power, so the graph will be a straight line. And it's enough to know only 2 points that lie on the straight line to know the straight line, because through two given points which are distinct, only one line passes, exactly one line passes through two given points which are distinct. So it's enough to know just 2 points. Accordingly, we will just put two values of x and find the corresponding values of f of x. But we do make a table. So that table will look like this. Now, among the many possible values of x that one can take, there are two very convenient values which will help us draw the graph more quickly. So here we have x and here we have f of x. One of them is x equal to 0. When x is 0, then the function can be quickly the value can be quickly calculated. When x is 0, f of x is 10. Another value is that x value which will make this output 0. And that of course is minus 10. When you put x equal to minus 10, you are going to get the f value 0. Because of these 0 values, things become simple. Why? You see, when your x coordinate is 0 and y coordinate is something else, or maybe 0, who knows, I am talking about the general situation. If your x coordinate is 0, then the corresponding point lies on the y-axis. And when your y coordinate is 0, the corresponding point lies on the x-axis. That's why things are simple. Now, if you draw the graph showing all the points that you will mark on the axis and everything, of course, you will have to mark many points because you need 10 points above the x-axis to mark out this 10. Also, you need to go to minus 10 here. Here, however, I am not going to do that. I will just simply assume that, say, this much is 10 units distance from the origin on this side, that's why we have minus 10. And an equal amount above the origin will give me the point 10 on the y-axis. So when my x is 0, y should be 10. That means this should be a point on the graph. Similarly, when my x is minus 10, then y is 0. So this is another point on the graph. And we know from previous experience that the graph of any such function is a straight line. And that's why this will be the graph. Okay, so perhaps I should not have written minus 10 here itself. because it interferes with the graph. So it's better you draw the graph first and then write this point minus 10. The line of course extends indefinitely on either side. Okay, it does not end. Now what I said just now, it's not exactly necessary that you have to show all the points 1, 2, 3, etc. because you need just minus 10 and 10. In other words, you just need a 10 unit distance. You take any distance to be 10 unit distance, the 1 unit distance will correspondingly be fixed then. Okay, it will be 1/10 of this distance. So in this way also if you show, that's fine. There is nothing wrong with this. You will, however, have to write those things. Let us take x equal to 0 and x equal to minus 10, or taking x equal to 0 and x equal to minus 10, we get the following values of the function f of x given by this table, by the following table. And so using the table, the graph of the function is as follows. Keep in mind though that you may be expected to put more points, because here we are using the fact that the graph of any such function is a straight line. However, I think it's better to show say 2 or 3 more points so that one can see that yes, the graph is a straight line. Although no matter how many points you take, there still is that question which remains. For example, say here I am saying that the graph is a straight line, but what is the guarantee? Say instead of taking these 2 points, you take 100 points. But in between those 100 points, there are other points also. So who knows, maybe the graph goes through them like this. But in between, the graph oscillates. That cannot be answered right now. You have to take it for granted that the graph of any such equation is a straight line. But still, instead of showing just 2 points like this, you can show a few others, 2 or 3. Okay, this of course is not a part of the graph. The question I raised just now, that what about the portion of the graph in between those points? How do we know that the graph will look like that in between those points where we have not actually plotted any points? That cannot be answered right now. That can only be answered when one learns calculus and sees what derivatives are. Okay, so we will get to those things, but not now. Instead, let us see what comes next. The next one is about a relation. So here we have let R be the relation on Q, the set of rational numbers defined by this. That means R will be a subset of the Cartesian product Q times Q. Okay, that's what it means for R to be a relation on Q, or in other words, a relation from Q to Q. So it's the set of all ordered pairs of rational numbers such that, what is the relation? Such that their Oh, so in the book they have taken a comma b. It does not matter. I can write x comma y such that the difference of these two rational numbers is an integer. Show that we have to show three things. The first one is, because I have written x comma y, so let me use x and y and z. This belongs to R for all rational numbers x. We will solve this example first and then we will have a quick discussion about the conditions that we are going to prove here. For all x in Q. Number 2. If x comma y is in R, then y comma x is also in R. Number 3. If x comma y and y comma z are in R, then so is x comma z. We have to show these three things. So let's show them one by one. Yeah. So first we have to show that for any rational number x, this ordered pair belongs to R. But that's rather easy. For any x in Q, we have, all we have to check is the difference of x and itself. If that difference belongs to the set of integers, then x comma x will belong to R. So what is the difference? The difference is 0. 0, the rational number 0 is of course an integer. So this is in R. Okay, so that is number 1, part 1. I think I have mentioned this relation somewhere before, maybe in the exercises. Oh, I think, do you remember that I gave you one bonus exercise which I did not really solve? There I think I have this relation. Number 2. So it's given that we have this. Since the ordered pair x comma y is in R. So by the condition of R or by the definition of R, the difference x minus y is an integer. But this implies then that y minus x, which is nothing but the negative of x minus y, is also an integer, because the negative of any integer is also an integer. Thus, y comma x belongs to R. And then the third one. Since x comma y and y comma z both belong to R, we have x minus y and y minus z in the set of integers. But if you add two integers, and keep in mind that these conditions are not trivial, because we are not saying that x and y are integers. No, x and y are some natural numbers. Rational numbers. But their difference is an integer. If you ask me for an example of two rational numbers which are, say, not integers, but their difference is an integer, so I can give you this example. Say you take, let me just digress for a moment and show a little example of x and y which are themselves not integers, but the difference is an integer. You can take this simple example. Say you take x equal to 3 over 2 and y equal to 1 over 2. If you calculate this, you see that it's 1. Okay, so individually none of them is an integer, they are non-integral rational numbers, but the difference is an integer. So that's why you cannot assume that x and y these things are integers, only the differences are integers. But both of them are integers, so their sum will also be an integer. Hence, this is also an integer. But what is this sum? This sum is nothing but x minus z. So, x minus z belongs to R. That is, x comma z belongs to R. That's what we wanted to show. Now, these three conditions may seem like somewhat arbitrary. Like someone may have noticed that, these things happen for this relation, so let's make that itself a question. Fine, but these conditions are not arbitrary. In fact, they arise very frequently in mathematics. And a relation which satisfies these three conditions has a name. Such relations are called equivalence relations. We will see this, we will study this more about this in second year. Second year means in 12th standard. But right now itself, it doesn't harm to at least know the name. Say you have a binary relation. Here, the relation is on the set of rational numbers. But in general also, you can consider a relation. Say, A is a set and R is a relation on A. So that means R is a subset of the Cartesian product A times A. Suppose R satisfies these three conditions. Number one, that A comma A belongs to R for all A in A. Okay. Number two, if A comma B belongs to R, then b comma a also belongs to R. And number 3, if a comma b and b comma c belong to R, then a comma c also belongs to R. And you have to understand that since we are considering these ordered pairs to be lying in R, to be elements of R, so these components A, B, C, all these things are elements of A. Then R is called an equivalence relation on the set A. These relations are important in mathematics and they help us do something. Okay, not going to go into the details of those things. There's time for that. Right now, you just note that this is something we are going to see more about in future. Besides these conditions, individual conditions themselves have names. This condition is called reflexivity. A relation which satisfies this condition is called reflexive. This one is called symmetry. It's obvious why this is called symmetry, because A comma B, B comma A. And a relation which satisfies this condition will be called symmetric. And this third one is called transitivity. And a relation which satisfies this will be called a transitive relation. There are relations which satisfy say only reflexivity but not the other two, all possible combinations. There are examples, okay, supporting those cases. That means we have seen above an example of an equivalence relation on the set of rational numbers. And this relation relates to rational numbers only when their difference is an integer. So let's now see what comes next. Equivalence relations are, in a sense, a generalization of equality, ordinary equality. There was one remark which comes after the first example that I forgot to mention, but you can see that in the book. I mean, it's about, it just says that functions of the type f of x equal to mx plus c, that is linear functions in x, they are called linear functions. That's what that remark is, and these functions all have straight line graphs. Okay, so what is the next one? Let a set is given. A set of ordered pairs of numbers and there is one more, -1, -3. All right. Be a linear function from z to, okay. Let this be a linear function from the set of integers to itself. Find f of x. Oh, because in this example the term linear function has been used, so that means I have to write it formally. Here itself I write the remark before we start the solution. A function Do you recall that after discussing, after defining relations and after going through the few things about a general relation, we actually mentioned two special types of relations. One of them is an equivalence relation and another one is an ordered relation. So this was that. Okay, not going to say anything about ordered relations in general. Okay, that will be too much. But equivalence relations we will see next year. But anyway, right now let's define a linear function. A function if from R to R defined by this formula or this rule that f of x is equal to mx plus c, where m and c are real numbers, arbitrary but fixed real numbers, then f is called a linear function. Okay, I cannot simply say this and move on to the solution of this. I need to say something else. Does it feel like this m and c are also actually not constants but variables? Because you can take m equal to say 1. Now nothing prevents you from taking m equal to 2 as well. Okay, in another case, say another value of m will be 2. X, however, is considered as variable. So if m value is changing, x is also changing, then what is the reason for saying that m, and although we haven't written it here, but in the book you will see where m and c are constants. In what sense are they constant? If we are not writing something, some concrete constant, say I write 2 in place of m and say 3 here, 2x plus 3, then it makes sense to say that 2 is constant, 3 is constant, but x is variable, because in place of x you can put many values, okay, any real number. Actually, the sense in which these quantities are constants is that you have to make a choice of this. They are also variables. Strictly speaking, they are not the type of constants that 2, 3, these things are. Okay. M and C are also variables, but they are a different type of variable than X. You have to make a choice for M and C to have a function f here. Say you choose m equal to 1 and c equal to 3, so that your function now becomes x plus 3. For that choice of m and c, x then can change, but that choice will not change with x. So when you encounter constants like this, which are not true mathematical constants but seem to be variable, but in the sense that you have to first make a choice of those variables, and then depending on that choice you get one function where then x varies usually. Such constants are called arbitrary constants or parameters. Okay. What they are called is not really that important. It's important to understand in what sense they are constants. Once a choice of m and c has been made, then you have one function. So what you are looking at here is actually not a single function. It is rather a family of functions where there are many members. Each member corresponds to a value of m and a value of c. But within a single function, x of course keeps varying. Okay. So that is why due to this difference in the nature of the variables m and c and x, this m and c are called parameters, whereas x is simply called a variable. Okay. Now let's see the solution. So we are given a function. A function, after all, is this is a very strange way of showing a function, but it's technically correct. A function, after all, is a relation. So one can write like this. So what it says is that the first coordinate is of course your input x, and the second coordinate is the output f of x. Instead of writing like this, you can also write f of 1 is equal to 1, f of 2 is 3, f of 0 is minus 1, and f of minus 1 is minus 3. Same meaning. In fact, let's write that. We have f of 1 is 1, f of 2 is 3, f of 0 is minus 1, and f of minus 1 is minus 3. But the additional information is that it's a linear function, which means that it will have this form, its formula. Since f is a linear function, there exist some real numbers m and c such that f of x is equal to mx plus c for all x in R. Now, using this information, we have to find m and c. Actually, only two equations will be enough. Let us use this one, f of 0 equal to minus 1, because you have 0 here, so we can quickly find things. Now, f of 0 is equal to minus 1. So, c is equal to, not like this, m times 0 plus c, of course, because c is 0 plus c. And this is nothing but f of 0, and that is minus 1. So from this we have simply got c. So we now know that c is minus 1. Now let's use this one. It's not actually there is no hard and fast rule that you have to use this one or this one. It's up to you, whatever you find convenient. Now, 1 is equal to f of 1. F of 1 is m times 1 plus c, but we already know c, which is minus 1. So, we get this equation, 1 is equal to m minus 1, which implies that m is 2. Oh, I should have kept these things. But anyway, we can write it once more, which implies that m is 2. Hence, so we have found m, we have found c, so we can now write the function. Hence, f of x is equal to 2x minus 1 for all x in R. Now, I just wanted to show you that the other pairs of numbers also satisfy this formula. That's why I wanted that formula. So, what are the things we had? If we had f of 1 equal to 1, then f of 2 was 3, f of 0 was minus 1, and finally we had this also. Among these 4 equations, which are the ones that we used? We have used 1 equal to f of 1. We have used this, and we have also used this. So, there is nothing surprising that if you put in place of x 1 and 0, you are going to get 1 and minus 1 respectively, because these equations have been used to find m and c. But what about this? Say you put x equal to 2. 2 times 2 is 4, 4 minus 1 is 3, yes. So, this is also satisfied. Similarly, if you put x equal to minus 1, you are going to get minus 2 minus 1, so which is minus 3. Fine. Okay, so that's why only 2 pairs of numbers 1 comma 1 and 0 comma minus 1 are enough to determine a linear function. That's because geometrically these two correspond to 2 points in the plane, and exactly one straight line passes through 2 points, 2 distinct points in the plane. Whatever other points we have, their coordinate pairs will automatically satisfy the equation. All right. What do we have next? Find the, again, domain. Fortunately, we do not have to find range here. Yeah, those things arguably are quite tough at this level, finding domain and range of a function. But anyway, here goes the next example. Don't get scared, we only have to find domain, and it's not really that difficult. Find the domain of the following function. So the function is x square plus 3x plus 5 divided by x square minus 5x plus 4 So from the formula for the function, we clearly see that it's a rational function. It's a quotient of 2 polynomials. But anyway, it does not really matter if it's a rational function or any other type of function. We have to find the domain. Now, domain means the natural domain, the largest set of real numbers, the largest subset of the set of real numbers from which if you pick your input, then the output according to the formula for the function is also a real number. To put it extremely simply, it's that subset of real numbers from which if you pick your input, you can calculate output. You do not face any problem. Now the only problem that can happen here is to have 0 in the denominator. That's the only possible problem. So you have to identify those x values for which the denominator polynomial becomes 0. Or in other words, you have to find the roots of the denominator polynomial and then remove them from the set of real numbers. That will be the largest possible domain, or which simply is called the domain of the function. So let's see which x values make the denominator 0. We have, and this is your routine exercise. Either you factorize this polynomial or you use the quadratic equation root formula. It's really easy to factorize this, so let me just go for that. We have x square minus 5x plus 4, which is simply this. I mean, it doesn't take real effort to see why that is true. If you multiply out the terms, you get x square minus 4x minus x, that means minus 5x, plus 4. Okay. So 1 and 4 are problematic points. They have to be removed. So x square minus 5x plus 4 is 0 if and only if x belongs to this set. So the domain of f is the set of real numbers difference this pair set 1, 4. That's it. And there is one more. A partly defined function or a piecewise defined function is given. I think we have to draw the graph. Oh, but then I cannot write anything here now. Or at least I can write the function f is defined by what formula? F of x is 1 minus x when x is negative 1 when x is 0 and x plus 1 when x is positive. Draw the graph. Note that the function is kind of complicated, but the individual parts of the function are themselves linear functions. So in those parts of the domain, the domain is divided into 3 parts, right? You see one thing clearly, the domain of f is the entire set of real numbers, because there is no problem in putting any real number x here in this in these rules. If x is negative, then the output is 1 minus x. Fine, any negative x can be taken. When x is 0, the output is 1, and when x is positive, the output is x plus 1. There is no problem in taking any real value of in place of x and have an output. So the domain is R, but in different parts of the domain we have different linear functions. So there the graphs will be straight line, except at x equal to 0 because it's just a single point. So in the individual parts, we have to again figure out 2 points on the graph that will tell us what the straight line is. The book, however, I don't think does it that way. It just puts some points, makes the table or does not make a table, just some points. Points means coordinate pairs, input, output, like that, and then draws the graph. Let's just straight away go for the graph. Let me do it my way and then I will tell you what the book has done. So in the beginning itself, we have recognized that in each individual part, the function is a linear function, so the graph will be a straight line. But as a whole, the graph will not be a single straight line. So let me draw the y-axis first. Another advice when drawing graphs, if you are not really sure about what the graph is, I mean sometimes things will be familiar, say you have an equation about which you know roughly how the graph is going to look or in which part of the coordinate plane it's going to lie. So if, for example, if it lies here, then there is no need to draw the axis like this. You can draw the y-axis somewhat on this side because this part is not important. Here, however, I don't know how the graph is ultimately going to turn out. That's why I have kept room for all possibilities. Okay. Now, when x is negative, say I take x equal to minus 1. If I take x equal to minus 1, then this will be 2. So that gives me 1 point. Oh, so that means I have to actually mark these things out. At least 2 units distance from the origin along all the 4 sides. So when I put x equal to minus 1, it becomes 2. So this is 1 point. Minus 1 comma 2. Alright. If I put minus 2 though, then I get 3. So another point will be here. What if I put x equal to 1? 1 is positive, that means I have to use this formula. Then I get 2. Again, somewhat symmetric with this side. And if I put x equal to 2, then I get 3. Alright. And if I put x equal to 0, then I am going to get 1. Okay. Now, in spite of not putting any other points, can I say that this is my graph? and one more thing, these you should not put white circles here, okay? These are just some points. I just made them prominent. Can I just simply say that yes, that's it? Yes, I can. Why? Because I know that in the negative part of the real axis, the x-axis, this is the function. F of x is 1 minus x. That's a linear function where m is minus 1 and c is 1. So its graph is going to be a straight line. I already know that. And the straight line has to pass through these 2 points. So it can be only this straight line. This straight line will come as close as it can to the y-axis without ever touching the y-axis because x is less than 0. But at the same time, at x equal to 0, the value is 1. So this extra point also is a part of the graph. The same can be said about the positive side. The positive side is also a linear function with m equal to 1 and c also equal to 1. And the graph passes through these 2 points. So it should be only this straight line. It will also come as close as it can to the y-axis without ever touching it. But with this extra point joining these 2 things, this is the graph. So although the graph as a whole is not a straight line, but it's a combination of 2 straight lines. Okay, so that's the graph. Okay, let us now see finally what the book has done. The book has plotted some points. At minus 4, for example, they have calculated that the value is 5. At minus 3, minus 2, minus 1, all those things. And then also at 1, 2, 3, 4, 5, etc. And they have plotted those points and they have joined them like how we normally join plotted points and have the graph. But why go through all those things when we already know about linear functions and their graphs? But anyway, it's up to you how you want to do it. Whether you, instead of, keep in mind, if you do it like this, you will then have to write down those things that I have said. That on the negative side of the x-axis, it's a linear function. So the graph is going to be a straight line which passes through these 2 points. And the same thing and the similar thing for the positive side. Along with these 2 things, at 0 the value is 1. And that is why the graph looks like this. You will have to write that. Either you do that or you plot many points and then just say that yes, and that's why the graph is like this. So these are the miscellaneous examples. After that we have miscellaneous exercises. Those we will solve, and then finally the function chapter will be over. But anyway, that's just it for tonight. What do we have tomorrow? Tomorrow is what? Friday, no? So linear algebra. Okay, so see you tomorrow with linear algebra. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.